Now, I want to talk to you about something that's really, really, really interesting. And that leads you directly to somehow thinking about relativity. And it comes from the fact that light has a speed, and light has a different speed depending on what it moves through. So we call it the path length. What does that mean? Okay, so watch this very carefully. I want you to pay attention to this. So suppose you have 2 points, point A and point B, and there is a distance L between those 2 points. Now, L, in fact, is independent of the medium that I place in between them, correct? Mm-hmm. So I can put water, I can put glass, I can put air, I can put, I don't know, carbon paper, I can pick another cloth, I can put whatever I want in between them, and L will be independent of that. However, when light travels through point A to point B, it travels depending on what medium you place in between these two. Now, why do I say that? Because the speed of light is a constant. And we know speed equals distance over time. So the distance can't change. The speed of light cannot change. So what must change? Time. So the time it takes to travel between point A and point B must change somehow. Got it? Okay, so now let's write this down. Between the 2 points, L is independent of the medium. Doesn't matter what you place in it. Speed of light is also a constant. We know speed equals distance over time. So what must change if speed can't change and the distance can't change? We have to have a different time. So suppose T1 is the time it takes light to go from A to B when the medium is air. And T2 is the time it takes for light to go from point A to B when the medium is, say, water. And T3 is the time it takes if the medium is, say, glass. Now, by how much longer will it take light to go from point A to point B if the medium is air? And that amount, we say that it takes light n times longer to go from point A to B if the medium is air, and n2 longer if the medium is water. Where n is a number that we call the refractive index of the medium. Do you see how this word is progressing? Speed can't change, distance can't change, so time must change. And because time changes, we have to figure out how much of the time changes. So for every medium, we have come up with a number by which the time changes, and we call that number the refractive index. We have defined it, we have calculated it, we've put it down in a table, and all physicists use it. This implies that it actually takes n times longer for light to go from A to B when the medium changes. And that is just a number that we have calculated. N is called the refractive index of water. And it is also another number which is called refractive index of glass. So people have calculated it, they've put it on a table, and that's what we use. This helps us define what we now call the optical path length. So is time t2 bigger than time t1? So in air or in a vacuum, it will take the least amount of time. So let's say we put glass in there. Will it take longer time for light to reach there? That means, how do we account for that delay in time? We can also define another length to account for it. And that length is called the path length. So the delay in time for light to reach point B can also be accounted for if we consider another length, say S. Since we cannot change the C, like C is a constant, 3 times 10 to the 8 meters per second, and we define that path length S is defined as the normal L that we have times N. And from here, all of this results in the fact that refractive index is now defined as the speed of light in the medium divided by the speed of light in vacuum or free space. Now I'm going to give you another point of view. So this was a point of view of the length being changed, right? So we defined a new term called the optical length. But you can also do what is called number 2. Another point of view. So what if, instead of looking at it from the point of view of light, you are looking at it from the point of view of an observer that is observing the light coming towards them? It's going to be weird, but hang in there. It's going to make sense in a second. So imagine that you have a point A and a point B, and there is a person standing here. And this is a distance L. If there is nothing in between, what does this observer see? Light coming towards them at speed?
Light
C, right? Now, what about if I put in water in between here? Now, what will this observer observe? This observer actually observes object A through the medium with, pick a refractive index.
1.4.
No, like N1 or N2.
N2.
N2. Okay. With refractive index N2. Okay, fine, I'll just call it N. Whatever that N may be. Now, what happens to this observer? In reality, point A is still at the same point, right? This object is still sitting here. But the view of the observer has changed. It appears to the observer to instead be at point A prime, at a different point, okay? So to this person, to this observer, object at, say, point A appears instead at point A prime. That means, according to that observer is saying that that point appears at, say, L prime n distance through the medium. Whereas originally, when there was no medium, the distance was Ln0. That's without the medium. But as soon as I put the medium in, the placement of that observer changes. So that means the path length is actually different. So I'm going to say the path length has changed. And what is, when there's no medium, what is N0? 1 for air. However, I do know that in reality, both of these should be equal to each other, correct? Because the actual distance did not change. Right? The L didn't change, physically did not change. It's just that the observer observing it has changed. So that means I can write Ln0 is the same as L prime n. The actual distance is the same. Regardless is the same. Regardless of the fact that I placed a value in there or I did not. And when N0 is air, can I write this when N0 is air? Can I write this as L equals L prime n? Or may I write this as L prime equals L over n? And this L prime is called the reduced distance.